All right, I start recording. Hi, everybody. It's 8 p.m. GMT, and welcome to this new season on VSA Online. I'm very happy to see you all back. And before I give the word to Tony, who is the first speaker today, I want to make some clarification about the website for the webinars. So as you most likely noticed, so the old website is not accessible. And this is done on purpose, simply because my university terminated Google accounts. And so the old website was under the corporate account. And just not to lose any information, I migrated all the content to the new to the new account, basically. So what will happen in the future, because the old website is well indexed by Google, so I will bring it up again and see how long it will live after the contract termination, and you will see a single page redirecting to the new website. So that's pretty much it. So back to VSA Online. So I'm very happy that we were able to compile an exciting program until Christmas. So please check our schedule on the website. So the link you find here. And without any further delay, so I transfer the presentation right to Tony. And by the way, his slides are accessible online, so you will find a link on the website. Tony, the floor is yours, please.
Okay, thank you, Evgeny, and thank you again for setting this up. Can you hear me okay? Give me a thumbs up.
Yes.
Oh, okay. Okay, great. Okay, so what I wanted to talk about today actually came out of a question at a previous seminar in this series where somebody was mapping from lower dimensional embeddings to high dimensional embeddings. And during the question time, there were some questions around the properties of this. And during that time, I also suggested a potential way of doing this mapping. And some good questions came up around that. And I went and investigated it a lot more, and well, a moderate amount. And so what I wanted to do was just report on what I found there. So, the motivation for being interested in this, in mapping from relatively low dimensional spaces to much higher dimensional spaces, is that there's now a lot of embeddings available from various kinds of deep neural networks. And these are typically lower dimensional, sort of in the range of 32 to 256 dimensions, though in recent transformers, this is getting to very high dimensions. And the interesting, what makes these embeddings interesting and useful is that they encode semantics, so that similar objects have higher cosines of the vector embeddings that represent them. And but up until recently, these available embeddings were typically just much lower dimensionality, and VSAs tend to need very high dimensionality, much greater than 1,000 to work well. And the lower dimensional spaces are just not robust to random noise and to crosstalk noise. And so this is the motivation for wanting to have a mapping from lower dimensional spaces to higher dimensional spaces. And the last reason of being interested in this, just personally, is I just want to understand what's possible. So if we do have a mapping like this, then what are the properties that we want from it? I would say that one of the properties we want is that we're able to retain these similarity relationships, so that our mapping, so that if we map two embeddings from a low dimensional space to a high dimensional space, that the cosine of them is reasonably similar. And because we want to retain those similarity relationships that hold in the original embedding space. The other property that we want is to gain robustness to noise, to crosstalk noise and random noise of the higher dimensional space so that we can do things like bundling and binding. And I've just got the question here, are there any other properties that we want? To me, these are the two main ones, but if maybe at the end, if anybody has any ideas about what other properties are important, that'd be a great topic for discussion. Okay, so I've got a relatively small number of slides, but they are pretty dense. So I think I've got around 10 more slides in total. Please do feel free to interrupt, raise your hand or just butt in at any time. So I want to begin with talking about the setup, and I'm going to try and describe this so that it should be understandable in detail, because it's really not that hard. What when we're talking, the scenario I want to talk about is when we're adding together, bundling a bunch of vectors, and we want to be able to detect what is in the bundle. And this can be put as a signal detection problem. And the setup is that we're going to have this should be, I've got a typo here. It should be using m n-dimensional vectors. So we have a dictionary of, and here I'm using 1,000 vectors. And just call them A, B, C, D, etc. And we want to create a bundle of them. So X equals A plus B plus C plus D. And then we want to test whether a particular vector from the dictionary is in that bundle. And we're going to do that by computing a dot product or a cosine. Everything, all the vectors I'm working with are normalized. So dot product and cosine is the same thing. And overall, the different parameters that I have in these experiments that I'm going to describe are the dimensionality. So the dimensionality of the vectors, and I'm working with vectors between dimensionality 32 and 256. The number of vectors in the memory or the dictionary, and here I just worked with 1,000 for most of these experiments, and the size of the bundle. And here I'm just working with k equals 4. I tried a bunch of different things. That sort of all the scaling is as you would expect, but all the results here I'm going to just report are with bundles of 4 vectors for the most part. And then the number of trials is the number of times I repeat these experiments to test. So a trial is trying to see which vectors are in the bundle and which vectors are not in the bundle. So what I'll do in one trial is compute the dot product of the bundle against every vector in the dictionary, and then see if it makes the correct decision in all cases. So it should, there'll be 4 where it is, where a particular element of the dictionary is in the bundle, and there we're expecting the dot product to be above the threshold. And for all the other 996, we're expecting the dot product to be below the threshold. And then in these charts, what I'm going to show, I've got a couple of thresholds. One is the midpoint. I just choose the midpoint between the two means as a very crude decision point for the threshold. And the other is just a simple one that optimizes the probability that a trial is correct. And that one, you can see the rightmost gray line, which is going into the green, that's the one that optimizes the probability that the overall trail is correct, because we've got 996 samples from the red and only 4 samples from the green. And so in this particular case, where the vector dimensionality was 64, the separation worked out to 3.28 effective standard deviations, and the probability that the experiment was correct was 34%. Okay, so this is the basic setup. If anything is unclear, please chime in now, and then I'll go into more of the experiments. Okay, so here are examples just showing that the robustness of this increases with dimensionality. And again, this is pretty straightforward. And so now I have the four charts on the right, and these are just showing experiments with 4 different values for dimensionality, and everything else is the same. So with dimensionality just 32, which is lower than what we had on the previous slide, the probability that an experiment is correct is only 1.2%. So, it's really not working at that level. When we go to dimensionality 64, that's what I showed on the previous slide. The probability it's correct is now 34% with the optimal decision threshold. Go up to dimensionality 128, and now we're up to 94% probability that a trial is correct. Go to dimensionality 256, and we're at 100% probability that it's correct. And in this case, if we just use the midpoint as a threshold, we'd still be at 98% probability that a trial will be correct. And what you can see here, both on these charts and just intuitively, is that the probability of being correct is going to be related to this separation of the 2 distributions. And so that is what I'm going to use as a measure of noise robustness. So with the n equals 32, we had a separation of 2.3 standard deviations. With n equals 64, it went up to 3.2 standard deviations. And with n equals 256, it went up to 6.61 standard deviations. Okay, so that's the basic setup. And so now what I'm going to do is report on some experiments with using dimensionality, with using various kinds of dimensionality expansion, and look at how are these 2 properties that I said that I wanted to try and find, how are they preserved with different kinds of dimensionality expansion. And so what I've got is a mapping from the lower dimensional space to a higher dimensional space. And so I'm going to take my dictionary in the lower dimensional space and then just map that to the higher dimensional space, and then do the same experiment before. And this first method for doing the dimensionality expansion is just a random orthonormal matrix. And this will just project from the lower dimensional space to the higher dimensional space. And then I'm going to measure the properties of that. And I'm also going to look at how well similarity is preserved. Similarities between, I'm going to look at all these plots I show for the similarity mapping is between all pairs of vectors. So here's an example where we start off with the dictionary, where the dimensionality of the lower dimensional space is 32, and the dimensionality of the higher dimensional space is 128. And I just generated a random orthonormal matrix to project from the 32 to the 128 dimensional space. And then I did that experiment with the bundle decoding, with doing 1,000 trials with k equals 4 bundles and looking at what separation do I get. And the separation that I end up with is 2.3. which was pretty much exactly the same as we saw in the lower dimensional space. So basically, this did not enable us to use the robustness of the higher dimensional space at all. It just, in terms of the number of its noise robustness and the number of items we could bundle together and still have them distinguishable, it's just the same as in the 32-dimensional space. What it does, and unsurprisingly, if you go through the mathematics, it does a perfect job of preserving the similarity mapping. So whatever the cosine of two vectors was in the lower dimensional space, it's equal in the upper dimensional space. And this is just a plot that is showing that. And the only reason it's not perfectly, a thin line on the diagonal is just this plotting technique shows the density as the cloud. Okay, so that is the linear dimensionality expansion and showing the properties of that. And as expected, that did not, access the robustness of the high dimensional space. So next up, what I'm going to describe is the first version of a nonlinear dimensionality expansion, and this was the one that I had suggested in that discussion session early this year. And this is where what we do is expand the dimension just using some fixed random aggregation of the outer product. So we take some 32-dimensional vector, that's the dimensionality of the lower dimensional space, and we form the outer product of it with itself, and then just have a aggregation, as in adding random elements together, but always the same. This is a fixed mapping to end up with 128 elements. And when we do this, this actually has pretty good noise robustness. So it does access the robustness of the hyperdimensional space, which is good. And this was as expected. The separation there, so I'm mapping in this experiment, mapping it to 128 dimensional space. So the separation was 4.14, which is somewhere between the separation for 64 and 128 for the vanilla case. So, it didn't perfectly access it, but it did a good job of getting a lot more noise robustness and ability to bundle multiple vectors together by going to the high dimensional space. But the similarity preservation is broken. What I didn't realize when I suggested it was that you actually end up with this smile shape for the similarity relationship, so that things that had a negative cosine end up with a positive cosine, and overall it's very noisy as well. So that is not the properties that we want. We're losing similarity preservation. Okay, so to move on to the next versions, which are just going to be higher order versions of that. And I just want to try and explain this, looking at it in a slightly different way. So what I've got here, this grid of four by four circles is just showing this outer product, and then how we would add them if we're doing from a 4-dimensional space to a 6-dimensional space. This is what I described on the previous slide. We have the Y1 through 6, which in the 6-dimensional space are just the sum of random elements of this outer product. And so what I'm going to do is now move to higher dimensions and to higher order products. So instead of just an outer product, I'll look at third order essentially the third order tensor and etc. And then I'm going to do basically a random sum of elements from the third order sensor and represent that as a table where we've got 4 columns. The first 3 columns are the source indices, and then the fourth, which will specify one particular element of that third order tensor. And then the destination index is just where that ends up. And so we can have this table, and this specifies a way of doing this third order dimensionality expansion. And the result of that is it's starting to work. So here what I did was, again, the small dimensional space, the lower dimensional space has dimension 32, the higher dimensional space has dimension 128. And what I did was just make up a table of these random aggregations of order 3 elements from the tensor product, and there's 12. I picked 12 of these of these elements at random and summed them together to get the value in the 128th dimensional space. And when I do this now does have pretty good noise robustness. Again, now the separation with 128 dimensions is 4.52. So this was better than just the second order method, because the separation for D equals 64 for a bundle of 4 was 3.28, and for 128 dimensionally 128, the separation was 4.66. So we're getting pretty close to that 4.66 with 4.52, which was the separation that we achieved. And now the similarity preservation is monotonic, but it's not that strong, and it is still quite noisy. I would argue that the degree of noise here, I put some statistics. The correlation is just 20%, which is a pretty low correlation. If you're trying to predict the similarity in the high dimensional space from knowing the similarity in the low dimensional space, then your R squared is only 14%. If you're trying to predict, if you've measured the similarity in the high dimensional space and you're trying to predict the similarity in the low dimensional space, the original similarity, then your R squared is 6%, which is really, I don't think that's particularly usable. Okay, so that was version 2, and we can go to higher. I tried higher order versions of this. The even order versions all have that smile shape, and the odd order versions, are all pretty much like the order 3. So the next thing, and this is the last thing that I'm going to describe here, is just to mix these 2 techniques together. So just to mix the linear and the nonlinear dimensionality expansion, and going to mix use the third order where dimensionality expansion, and mix that with a linear dimensionality expansion, just that random orthonormal matrix, and using mixing proportions of 0.6 for the orthonormal projection and 0.4 for the nonlinear projection. And so now what we're ending up with is the separation. So the noise robustness is now at 3.88, which is lower than what we saw just for the nonlinear dimensionality expansion. As you'd expect, it's in between the 2. And so that's still reasonably good, and the similarity preservation is a lot stronger and less noisy. And the correlation is 63%. The R squared is in both directions is around 40%, which is getting two where, it's sort of beginning to be useful, but I'd sort of still be surprised, if the similarity relationships amongst our embeddings is important, then I'd sort of like to see this stronger. So here's some summaries of all of these results. The first four rows here are just the vanilla baseline and just showing what the signal separation is and the probability of being correct. So we went for the signal separation, went from 2.32 up to 6.61 standard deviations. And where we ended up with in using the mixture of the linear and nonlinear was a signal separation with the high dimensional space being 128. The separation was between 64 and 128. We did get the monotonic similarity preservation, and the correlation was just getting into a usable range. Okay, so that's pretty much what I wanted to report on here. So that the linear dimensionality expansion, it doesn't utilize the robustness to crosstalk noise provided by the hyperdimensional space, at least in the way that I was conceiving of it. It does completely preserve those similarity relationships. The nonlinear dimensionality expansion, it does provide very good robustness, especially when we use the higher order dimensionality expansion, but it did a lousy job of preserving those similarity relationships. And mixing those two, we got, average, sort of, you get the average. So it gives us some robustness to crosstalk noise in that we want to get from the hyperdimensional space, and it does a just okay job of preserving the similarity relationships. And so that's where I ended up with this. And obviously there's many ways that we could do this kind of dimensionality expansion. I suspect that what might work better, but would be a lot more work to construct, is something like where we have maps between the spaces that are locally linear in certain regions of interest, but globally nonlinear. And I don't know how to construct those, and I didn't try any experiments with them yet. But I think there's lots of potential things we could do. Okay, so that's basically everything I wanted to cover. I'm surprised I got through so many dense slides in only 25 minutes. So yeah, thanks for the attention. And if there's any questions, please go ahead.
Thank you, Tony. So, questions, comments?
Hello, I have a question. Tony, do you have any reason to believe that if you keep increasing the order of the tensor of which you do the random sum, that it will keep approaching the 128 dimensions? Because you were saying that from 2 to 3, it already improved, but do you think this will keep going? And maybe in the limit, it will keep, as close as possible?
No, I don't think that will help. I think once there wasn't that much of a difference between 3 and 5, and already with 3, the robustness to crosstalk noise was already approaching that of the higher dimensional space. So if you look at this one here, the third order nonlinear, which is this second last row, had the signal separation of 4.52 in the utilizing the 128 dimensional space, and the the separation just with the vanilla approach of completely random vectors had, just a separation that was only a little bit higher at 4.66. So there's not much headroom for improvement there, and the similarity preservation was no better. I wouldn't expect it to be better, and it wasn't any better with order 5.
But do you expect the 4.52 to approach 4.66 if you go higher in order?
Probably, but like I said, that headroom there, I'm not really seeing as that valuable, because you've already got like 90,
Right.
95 or more % of it.
I was thinking more from a theoretical perspective, whether that like you can guarantee
Yeah.
that it would approach that.
Also the other thing, the other parameter there is how many elements were used. So each element of the higher dimensional space was a sum of 12 third order randomly selected elements without replacement from the lower dimensional space. And you could increase that 12, and that's probably a lever that you could use for going higher.
Okay, thank you.
What would you expect there?
If it were going closer to the 4.6, you mean?
Yeah. Oh, I mean, yeah. If you went to the higher dimension, would you expect that it would get closer?
I'm not too. I would say my intuition on this is not very strong. But based on the two numbers that you showed, it would make sense to me that it would get closer. But
yeah. That's this is part of the reason I wanted to do it. This was to just develop intuition on what happens in these spaces.
I'm wondering. Oh no, you go ahead.
Thank you. So I may be wrong, or maybe I'm thinking about this incorrectly, but it seems like an impossible task. Maybe you probably knew that, because if you're projecting from a low dimensional space to a high dimensional space, you're going to be stuck on a low dimensional manifold. And so if you stay on that manifold, you can keep the angles, keep the cosine angles, maintain those. But of course, you don't gain anything. It's just using different representation. So the noise thing, you get the noise by basically moving those vectors out of the manifold, and that's what's destroying the cosine similarity. So I think if I understand correctly, you're basically looking for a compromise that's sort of going to get a sweet spot between the two different things that you're after. I wonder if like maybe not all cosine angles are equally relevant. Maybe you care mostly about them being close to 0, or you care about maintaining the high ones close to ±1, and you can sort of sacrifice some intermediate ones. Any thoughts on that?
Yep. Yeah. No, that's exactly my line of thought, and so that's why I was suggesting sort of a locally linear map where sort of things that we do want to be pretty similar, like say different colors or different different locations or different people, that it's locally linear for those regions of space. But then if we're comparing a color to a height, it's sort of irrelevant that the cosine of 0.2, if that flips to negative 0.1, it doesn't really matter. It's not interesting and not useful. And I think that's an interesting question of how you define which of those which of those cosines matter. And one approach would be to say, like you were suggesting, maybe just the high cosines, so the ones for similar vectors. Maybe that's all we care about preserving. and we don't care so much about the low cosines. Our mapping can be a lot noisier there, or maybe it's more to do with regions of space, like I was talking about. You know, there I just don't know what would be useful. Yeah, that's where we need to tie it to a real application to investigate the properties.
Yeah, interesting ideas. Thanks for the talk, Tony.
Mm.
Tony, I'm curious about this parameterization idea. Can one think about some like general scheme that maybe would be very easy to control between like linear and nonlinear? Have you been thinking about this mixed mode? Is it possible to somehow have maybe a single parameter node that could be controlled to control this linear versus nonlinear behavior?
Yeah, good question. Yeah, I don't know whether we could do something like like I just use that simple mixing of the two, but maybe that mixing could be a function of where you are in the space. But again, that's not something that I've had time to experiment with.
Yeah. I was just curious because it feels like maybe there is something. Yeah.
No, that's a great question, and that was something that I was wondering about, and I'm sad that I can't give a better answer.
Yeah, I think I have some sort of like kind of phantom memories almost that I think Okarasanen had like a number of years ago some paper that was probably going in similar, at least sort of I associatively recall the figures. There was some kind of very similar shapes of figures, like in terms of how similarity was changing. Maybe it might be worth taking a look at that paper.
Yeah. Can you say that name again?
Yeah. It's, let me try. I think I have somewhere.
I think it's like this in the channel.
Yeah. Okay. Yeah. I think I have the title of the paper. Yeah. It's Cognitive Science Meeting 2015.
Yep.
And actually, I'm thinking also about some phantom memories from around that times when Osgur used cellular automata for the expansion, but I'm pretty much sure it will be. Well, he never tested. I mean, he never performed this kind of tests. So most likely, it will be more of a linear type of projection or expansion. So basically, I mean, he has this article when he took an output from neural network and then expanded it to some high-dimensional representation and then did constructs, VSA constructs, and reasoning, analogical reasoning, like what is the automobile of the air or something.
I was wondering if you have thought about how this relates to the fractional power encoding, because you could maybe also do a dimensionality expansion by encoding each of your dimensions like a multidimensional fractional power encoding.
Interesting question. I hadn't thought about that. Yeah, interesting idea. I don't have any immediate intuitions about that, but that's something to think about.
At least then the vectors with very similar cosine similarity should remain the same. and then maybe vectors will taper to 0 more quickly. I'm not sure.
Yeah. So tell me more what you're thinking.
So let's say you want to go to some n-dimensional, higher dimensional space, then
Yeah.
and you go from d lower dimensional space. Then
Yeah.
you first create your d n-dimensional complex vectors, random vectors, or you just sample the faces easily, and then you do a matrix multiply with your input vector and the phase matrix, and then you do the sine cosine to create the complex vector.
Right.
So basically the fractional power encoding for each dimension separately, and then the dimensions bound together.
Yeah. Okay. Okay, cool. Thanks for the suggestion.
Yeah, I'm not exactly sure what would be the properties and how it would differ from what you've tried.
Yeah, I think I tried something similar. Moreover, not really the multiplying, but a phasor matrix, but rather, so what you might think, so you do this linear expansion, and then you take this, and then you treat this vector, the expanded vector, as phase, as a of a phasor. So as a phase vector, basically. And then you have this bandwidth parameter to control the way how your similarity decays.
Yes, exactly. This is how I ended up implementing it for the TorchSD library. That's why I was thinking about it.
Oh, okay.
So you will be working with complex vectors, but I mean this will be the effect. So the similarity will be preserved, but I mean so it will decay faster. So it will be more separable.
You don't even have to treat them as complex vectors. You could just concatenate the sines and the cosines, and then the dot products between these would also work.
Yeah, sure, of course, yes. Obviously, I mean, but I mean, it's same effect.
Yeah. Yeah, but if you want to keep like more the traditional neural network, if you want to somehow incorporate this into the LLMs like you were talking about in the beginning, maybe that makes more sense.
Yeah.
Yeah, I had a question. This is, first of all, this is a really fascinating talk, but I was wondering if you'd kind of looked at it as kind of the inverse of a data reduction, like when you have like a high dimensional matrix you want to cut down and visualize, right? There's all these very advanced methods for, kind of trying to preserve local and global information at the same time. And what we kind of have here is like the opposite problem, right? Where we have the low dimensional representation. We want to get back to that high dimensional space with kind of more noise. So I was wondering if you thought about kind of incorporating some of those like visualization methods or data reduction techniques kind of, but in reverse.
Yeah, no, another great question. And that occurred to me that this was sort of the problem in reverse of these data visualization techniques. And one of the salient differences is that those techniques are often used for visualizing, and so they want to reduce to just like 2 or 3 dimensions. And I don't know whether that makes that much of a difference, but but again, interesting direction. But unfortunately, I didn't try anything along those lines.
Right. Okay. Thanks. It's really fascinating to think about.
Yeah.
Any more comments, questions? Well, if everybody is happy, then I think Tony and I are happy as well, right?
That's right.
Yeah, so I think we had a good start. So thank you, Tony, once again for the great talk. Just a very, very short reminder that the next... Wait. Just a short reminder that the next webinar will take place already next Monday, not in 2 weeks, but next Monday, in 1 week from now. And after that, we will continue with a 2 weeks period. Yeah, but otherwise, so thanks for attending. Stay tuned. See you in a week from now. Thank you. Bye.
Okay. Thank
Thanks,
you.
Tony. Great talk.
Thank you. Bye.